Okay, so in our last lesson, we looked at extracting metals from ores, and we're looking at alternative methods for extracting from ores today. Some of these include using electrolysis. We'll go into more detail about what that is, and we're going to have a look at using biological functions. We'll look at bacteria soaking up metals as well. So if you've just joined us, please, if you've got any questions, guys, use the chat only for me, please. I don't want to have to kick people out, but it's for me only. So you should be able to see the lesson on the right-hand side. And the whole purpose of this, like I just said, is I need you guys to be able to recall, where's my pen? Recall what an ore is. Okay, we're going to go into a bit more detail again on that, just to reaffirm that you picked up what it was. We're going to have a look at how some of them are extracted, heating it with carbon. Okay, carbon's readily available for it. And we have a look at how we use electrolysis and what electrolysis is. So the key to this, guys, is to take really simple notes and write those keywords down. So I would say have the word electrolysis written down. And from that, you can just draw little notes off what electrolysis is. You can put heating with carbon, why we do that, etc. Extract, I forgot, biological methods. There we go. I'll put that down here as well. And you can just draw little offshoots. So yes, it looks like a little bit like a mind map, but it's a good way of learning when we're online and doing it this way. Okay, so what are these? So if we were sitting in class, I'd just get you to start guessing what they all are. That might be a little bit unfair, but this is how rocks come out of the ground. So if I sent an excavator and a rock truck down into a mining pit, they would come out with rocks that look like this. Now, obviously, they're not very useful to us in this stage, but we want to extract the certain metals out. And what I'll do is I'll just click on the next slide, and it should start telling us. So we've got aluminium. Doesn't look like aluminium, obviously. Iron and titanium. Okay, copper. Now, these are all metals that are really important in your life. Most of you will be sitting around with some sort of smartphone. Aluminium, nickel, tin, all important metals in making up smartphones. Iron, so there'll be steel in your house that holds parts of your house up, and iron is a key component of steel. Titanium, any of you who are unfortunate like me to have metal plates in you at some point have titanium usually, or stainless steel, which again links back to iron. And copper is probably the most prevalent one in your life without you really realizing it. Pretty much everything you take for granted around your house is based on copper. Or the piping for the hot water system. When you turn the tap on and water comes out, it probably comes through copper at some stage. You might have plastic piping in your house. Depends when your house was built. Telephone lines, power cables running around your house, all are big users of copper. It's one of the reasons why copper is one of our most recycled metals, precious metals. And at the moment, it's about 4,000 pounds per ton. So for every 1,000 kilograms, you'll get about 4,000 pounds in cash for recycling copper, which is probably one of the reasons it gets stolen more than it should do. Okay, so some metals are pure. Now, this will be quite important later on when you're doing the little quiz I've set you. And if they are pure, it means they are non-reactive. Because if they were reactive, they wouldn't be found pure. So, sorry, I'm trying to write on a screen that isn't quite to scale, so apologies for my quality of my writing. And a good example of that is gold and platinum. And if you dig gold out of the ground, it comes out of the ground as gold. It might need cleaning up, but it won't be chemically bonded to anything else. All our other more reactive metals are things like sodium and potassium. They're so reactive you would never find them in the environment on their own. And a good example of that is obviously copper. It will react. Often we've got down the bottom here as a carbonate. Okay, and the good news is it's quite easy to get that out. It's expensive, but it's easy to get out. Oh, there we go. Get another picture. Right. Now, we've already talked about the reactivity series, and you should have the reactivity series written down. Okay, it's in the video I've linked to you in the last lesson. So go back and get the reactivity series if you haven't got it. But in this instance, we're now looking at extracting metals that are more reactive than carbon. So carbon being here, anything more reactive, okay, we're going to use electrolysis to do that. So remember, I got you to write electrolysis earlier and circle it. This is when you start putting some of those arrows and words. The first one, I'll split it in half for you. Okay, I'll literally, excuse the pun. We've got split. So if we split it into two parts, electricity for electro and split lysis. So electrolysis. And we use this as it's a great method. It's expensive. It uses electricity. It uses a lot of it. Electricity is very expensive when you're using it industrially. We don't pay for electricity at the same price that you pay in your house. It's roughly 4 times the price, depending on what kind of industry you are and what kind of tariffs you have, etc. But it is a great way of extracting metals, particularly our more pure metals that we need to get out from liquids. I'll go into a bit more detail on that. Okay, and there you go, straight away. Electrolysis when molten. Now that's really, really important, guys, because in molten, is it solid, liquid, or gas? Well, of course, molten means liquid. Okay, you cannot use electrolysis. Well, I don't think you can use electrolysis on a gas. I don't think anyone's ever tried. Or they have tried and not survived or succeeded. We're talking about liquids here. So you need to, whatever you're trying to extract needs to be in a liquid form first. There you go. It is extremely expensive. So cost is a factor. So that's some of the key points about electrolysis. And when we get back to school, we'll hopefully get the opportunity to do some electrolysis. We'll give you some mixed up ores and get you to split them into their key components. It's pretty messy, but you'll end up with something pure at the end, hopefully. Okay, so when we've talked about extracting metals that are more reactive than carbon, if they are less reactive than carbon, okay, we're going to what we're going to do is we're going to press the button. We're going to heat things up. There you go. You get a nice little fire sign. So we take our copper carbonate and we heat it up, and that's going to give us a copper oxide. Okay, so the oxygen in the air that we're adding. So this should really be like there, and there we go. I'll press the button, and we get our carbon dioxide. So we end up with a CuO plus CO2. Which were all originally part of here. So I'll try to do this off the top of my head. I think copper carbonate is 3. Yes, it must be. So then we split into our 2 components. Now, straight away, some of you will recognize that as a greenhouse gas. This is why it is not a particularly nice thing for the environment. So please make sure when you do extracting less reactive than carbon, you do a little arrow away, bad for environment. Okay, and straight away I was talking about things like copper, which we need lots of. Other things, we'll get onto those. I think they're on the next slide anyway. Now, what is this reaction called? I think this is going to appear. Here we go. Thermal decomposition. So on here, on your less reactive than carbon, great term, thermal decomposition. Now, I'll be honest here, I'm a physicist by trade. And when I teach thermal decomposition, I don't usually use metals. Ironically, I use pancakes. Because one of the things we add to pancakes is raising agent, or as you probably know it, bicarb of soda. And if you add bicarb of soda to pancakes, as it thermally decompositions, carbon dioxide bubbles are released, and you get fluffy pancakes. That's where the fluffy pancakes come from. Or you can use self-raising flour, which has the same thing in it. So I usually get my class to cook pancakes with and without our thermal decomposition. You get very, very flat pancakes, or you get really fluffy ones. I wouldn't suggest eating them, though, if they're cooked in a science lab. The test for carbon dioxide, some of you will recall this from earlier in the year. Hopefully you've looked at lime water. And if you pass carbon dioxide through lime water, it goes nice and cloudy. That's a fairly common test for carbon dioxide. It's a really handy one to have in your notes too, because almost any extended question, so if you get a 2 or 3 marker that talks about carbon dioxide, mentioning lime water as a test method is almost always worth a marking point. Oh, very much. Oh. Come on, slide, you can do this. Okay, so down the bottom there, it's asking us one more question. Carbon is more reactive than copper, so it can be extracted by its ore from heating. Okay, that's one of the things we've already covered. Okay, so reduction reactions. So extracting metals less reactive than carbon. Okay, so in this instance, we've got our copper oxide. So we've got ourselves to the next stage. So we've got copper oxide, and now we're going to introduce carbon into the mix. So this is almost like stage 2. So I've got my copper oxide here. So if you want to write this down, we've got copper oxide, and we're going to add carbon, and we're going to end up with something. Well, hopefully it's pretty obvious what we're going to end up with. And if you want to pause the video, and well, you're not watching it live now. If you're watching it live, you can't really pause me. But if you're watching this video later and want to have a crack at this before I press the button, please do so. But here we go. Oh, it's very interactive, this one. Okay, so the carbon replaces the copper, and this is called a reduction reaction. Okay, so I sort of alluded to that earlier. So on your notes, write down reduction, reaction, and put some key points about what a reduction reaction is. So we are replacing less reactive metals with carbon. Okay, so the less reactive and carbon are changing places. So we add lots of carbon to it, and usually you have to heat it up, and that starts reaction. Now, if I've got carbon and oxygen over here now, that means I've got, hang on, I don't know if this is going to clear off. I won't press it. Oh, I knew that was going to happen. I'll go back. Right, so carbon and oxygen. If I've got carbon and oxygen over here, that is now CO2. Okay, so if I cross C and I cross O2 off, I've now got copper, I know it's in red, all on its own. This is valuable. Now, the only catch is, of course, I've damaged the environment considerably by extracting it from its ore. And we do this on mass scale, industrial, and because we need lots and lots of copper in our lives. And one of the nice things about science as we improve technology is now with the rollout of fiber optic cable as a more prevalent source of communication. So when they're burying phone cables in the ground, they tend not to be copper anymore, they tend to be fiber optic cable. There are some drawbacks to that. There is plastic sheathing around, etc. But it does start to reduce our need on copper. Okay, oh, I said you needed this early in the lesson, which is good. It's in here again, just to remind us. And I won't ask you to do this again now because this was something we did in the last lesson, but the fact that it's come up in 2 lessons in a row will tell you how important it is. Please make sure you have this reactivity scale written down. You need to be able to recall where things are on the reactivity scale. And I've asked you some questions in the quiz after this lesson, which will ask of you where things will happen depending on where they are. And obviously this lesson's been a lot about where carbon is. I think we talked in the last one a bit about aluminium and zinc. And this is just showing how all the metals we need to survive in society, how they're all extracted. Okay. Oh, there you go. So now that you've seen that, this will be in the video later if you want to go back and watch it. I'll put it up on YouTube, and you can. I'll send you a link to the video. So if you just want to have these down as key points, but we've already written down electrolysis, and we've already written down it's molten. We've already looked at carbon, so using decomposition, and we looked at these two obviously being as found as pure. We don't have reduction there, but that's okay. Right, so I'm going to obviously fly through this for the sake of the people on the live lesson, but if you're watching this as a video, pause it and have a go, see if you could get these answers out. What I'm going to do is fly through, and I'm going to come back and ask those of you in the live lesson now. There we go. I went through it fast enough, I think. Right, biological methods for extraction. Now, this is quite quite an old idea. It's still used a lot in gold mining and copper and zinc mining. I was quite surprised to see it being used a lot in the Australian outback, where they have big piles of low-grade copper ore. So these are big mounds of, and they're just not worth processing in the traditional way. So normally where they would heat them up and add carbon, it's just, you don't get your money's worth back out. It's bad for the environment, etc., etc. So they don't issue permits for anyone to do it. So one of the processes is actually growing and circle phyto extraction, and you grow plants on these big mounds. So you have to excuse my drawing. I am not an artiste in any way, shape, or form. You grow these plants, and this is probably the bad bit for the environment. Then you burn the plants. You end up with copper oxide. And we've already talked about how to get copper oxide out. Then we can use electrolysis. So the idea is turning this low grade into a pile of, I suppose you'd say, high grade. Okay. Now the other side of this is bioleaching. Now I've never seen this done, but apparently it's becoming more and more usable. Again, same reason, it's better for the environment, easier to get a license and permit to do it. And instead of growing plants, this time around, we're growing bacteria, and specific bacteria. They have to make this work, they have to move all of this ore into like a pond. So if you can imagine, sorry, I am drawing 3D badly. Okay, so you basically put a big swimming pool, plastic tarp size thing down, and it's a you have to have the right amount of water and saturation. You grow bacteria on your ore, and then what you do is you start flushing that water through the ore, and you end up with this solution, which then again you can straight away use electrolysis. So these are two really good, more economical ways for, again, just to point out though, this is not what you do for high grade, this is for low grade. Okay, there we go. And if you want to go back and read that later off the video, go for it. I appreciate I've just drawn all over it. Okay, so this table down here, guys, is what you need to have in your notes. Okay, and what I'm going to do now is I'm going to pause the video, so stop the video. No, I won't. I can't do that. I'm going to go onto the next screen quickly for those who are watching it back later on video, so you've got the answers. But do pause it if you're watching this on video, and then try to work out which ones would fit as advantages and which ones are disadvantages. Once I'll flick forward and show the answers out. Okay, and then I'm going to go rapidly back and stop the recording so I can talk to the live students. Thank you very much for joining us. If you're watching this later on video, live students, stay with us.